Okay, so hi everyone. So today I want to talk about securing AI ML workflows and packaging AI ML applications and running them in the Kubernetes environments. Some challenges, some interesting problems we run into at Chainguard, and some of the interesting solutions that we've hopefully done for them. So my name is Wojciech Kocjan. I am a senior software engineer at Chainguard. I live in Kraków, Poland. This is my email and this is my GitHub handle. I'm also on the CNCF Slack if you ever want to, and Kubernetes Slack as well, so multiple Slacks. If you want to reach out to me after this talk and chat about some of the problems mentioned here or anything like that, feel free to do it. I'm usually trying to check my Slack, and I have it on my phone. Right, so AI ML and containers, right? So there's quite a lot of fun problems that we run into there. And I'll start with a brief description of what containers are. I think everybody knows this, but it's really interesting in this aspect. So, I mean, the whole concept of container is that we package a subset of the runtime without the actual kernel, but the runtime libraries. And the idea is that this is portable, scalable, efficient, it's isolated, it's reproducible. But also one thing that's not in this slide is when we think about containers, they're usually quite small. When you think about, I don't know, your Golang microservice, this would be a few megabytes of a binary, maybe some SSL certificates files, some basic operating system libraries, and that would be it, right? But then when we think about AI ML images, it's a very, very different world. So the first problem, the challenge that we noticed when we started packaging them is the size, right? So as I said, I'm used to the idea. I was using, I don't know, Argo CD, a lot of tools that would be Golang based or even other languages based, but they would be small. It would minimum. Packaging them or just running them would be very easy. There would be very little dependencies, and usually other than the Linux distribution, there would be very little vulnerabilities as well. It would be very, very easy to just keep them running, update them when needed, when there's a new version coming out where there's a vulnerability. It's just easy. And AI/ML is basically shipping everything. So we'll talk about what everything is in a bit, but it's quite normal to see images that would be several gigabytes in size. And keep in mind, I just mentioned Golang could be a few gigabytes, like a small Golang Hello World application would actually be a few gigabytes, so 1,000 times less. And one other thing that was really interesting that I didn't think of until this is specifically about PyTorch. I'm going to mention PyTorch a lot. It's my fun project to be working on it. There is this combinatorial explosion of all the things that come into the image. So one thing is the application itself, and with PyTorch, that's not just PyTorch. I'll have a slide on that as well. But it's like which features of PyTorch. There's a ton of libraries, so there's also which features of those libraries. And just as an example, if you ship anything like an ImageMagick or any other library, there's like 100 configuration options that compiled out for us as well. Then there is Python, right? I have a slide on that. I suppose there are 5 currently maintained versions of Python 3. And with AI/ML, a lot of code bases are complex enough that you can't just keep on switching to the latest Python version, especially if you're also running your own code that may not be easily portable, or some packages may no longer be there. Like you need to, in many cases, just need to do some updates to your code to have it running on the latest version. And GPU support, again, I have a whole, probably slides on that actually, and it's another difference. So if you build, say, TensorFlow, just to make it a bit different, TensorFlow is built a bit differently for CPU and GPU-based workloads. So this is also like two separate worlds that need to be dealt with. And on top of that, with GPU, there's also hardware support. So, for example, in many cases, the versions of the NVIDIA drivers, when you think about NVIDIA CUDA, they're tied to the hardware that's being run, or not all the drivers support all the hardware. So there's this whole matrix there also with what's supported. And there's also Intel versus ARM, which is a very recent, well, not recent problem, but I think nowadays it's more of a popular problem than it used to be, right? So as a fun thing, I tried to ask AI to generate what an AI/ML container would look like, and this is what it came up with, and I think it's quite accurate. So yes, it's bigger than anything else in the room. There's a lot of fans that are not fully working, and there's something outside the containers, which is the integration with the host drivers and everything. So I think that was quite accurate. Right, so, okay. So as I mentioned, size was the first problem, and with size, we also can talk about minimizing the number of CVs. It's not always 0, but it would be the ideal goal. And we can talk about some of the problems, right? So reducing the image size, okay, one obvious thing is the more you disable, the smaller the image gets, because if you just package the bare minimum application, it should be much smaller. But in many cases, it's not as simple as that, right? So we did manage to get one of our images down by around half, which is, I think the number is quite accurate. It was from 12 gigabytes with the upstream image down to 5. There were some things we removed, but it's kind of an interesting. So when we started packaging, this is again specifically PyTorch, we tried to figure out what's the minimum set of features in the image that we could ship so that our customers could use it. And then we tried to decide, okay, if this is not enough, maybe we should also start including some other features. Or this is kind of like an iterative process; it never finishes. But this is exactly the question here. Like, how do we decide that? And the answer was, let's start with something a bit more minimal and start adding things once we have requests for that. And there is also another problem that I probably should spend a bit more time on, which is PyTorch again is a slightly different beast when you run it on your own, which, for example, we do have a PyTorch image, which is just PyTorch. But also there are other applications like Triton, and I don't remember which ones right now, but I believe there were at least 2 that we looked at that also ship PyTorch. And with Triton, I believe, I don't know if this is still the case, but the PyTorch had to be patched, and also the set of features in PyTorch may differ. Like if you want to run it on its own, it may be a very different PyTorch that goes into the Triton, into an image that also ships Triton server. So there is a lot of challenges around features, and I'm not going to give you one answer. I'm just going to mention that a lot of it is trial and error, and I think we've done a reasonable job of trying to get it to a set of features that work for most cases. But it's like we're still evaluating how do we do that, which ones do we enable, which ones do we not enable. And the size and like reducing features and everything brings us to the next topic. So, I mean, at Chainguard, we try to package applications with as little CVs possible, ideally 0, but if not, then at least a very low number of CVs. And again, when we are shipping the whole world, and when we are basically including a bazillion libraries, Python with its own dependencies as well, and Python libraries, it's very challenging, right? So in one of the cases, by trying to reduce those things and also just trying to package things a bit differently, we got to a point where we had an image with 0 CVs. In some of the images, it may be much less than upstream, but we got that image that was over 1,000 CVs that I mentioned earlier to 0, which was quite a successful thing to do. And the way we've done it, and I believe there's another slide for that as well, is at Chainguard, we ship our own Linux distribution called Wolfie, which is basically designed to be more fitting for the cloud-native era. And what we do is it's using APK, so the same package manager as Alpine. It's using glibc, which makes it a bit faster. Like compared to Muscle, it can be even 50% faster in some cases, but in general it's a bit faster. And what we do is, instead of having like releases twice a year and LTS releases every 2 years, you have a rolling release that ships all the packages all the time. And for most packages, it's basically whenever there's a new version, even without any security changes, just new functionality, as long as it passes all of the tests, then we update those packages within 24 hours. Well, okay, that's not the SLA, but it's our goal to package them as soon as possible. And with that, for example, when we ship PyTorch, we would be having the latest version of ImageMagick, we'll be having the latest version of all the system libraries, and that on its own helps a lot with CVs, especially, again, when we are shipping a very large number of libraries that come with Python and all the libraries, and like image processing, video processing, audio processing. That is shipping a lot of dependencies. And again, by reducing the set of functionality and trying to focus on the minimum working image with enough features to satisfy our customers, we also reduce the CVs, because again, we may not be shipping all the dependencies that would be shipped otherwise. So that helps a lot. And again, every transitive dependency, so like Python package for image manipulation may depend on ImageMagick, which may depend on some other libraries as well, will help with reducing the number of CVs. So it's an interesting battle where we try to decide on the minimum set of features versus the actual usable functionality of the app, and it all is like this. And I'm talking a lot about PyTorch because PyTorch is what I've spent a lot of time on and trying to figure out some of the aspects of PyTorch and the version manage and the versions and the features there. But it applies pretty much to all of the AI/ML applications, and the more complex the application gets, the more checkboxes, tweaks, and settings that apply to it. Right, so apps, features, versions. Let's drill down into what I mentioned previously, right? So so this is me or anybody at Chainguard trying to decide how to package any of the apps, right? And again, PyTorch, just because I know it. So on its own, it's quite large, and this is the core package. But there's also a lot of packages related to or separate applications, we could even say, because they're quite large, related to specific features like Torch Vision, Torch Audio. I can't remember anything else from the top of my head. There's a few of them, and each of them is quite large. Each of them has its own set of dependencies, and some people may want to use it, some people may not. So it's a challenge which ones to pick, right? PyTorch is not okay. I'll introduce what version streams is. Version streams is an idea often found in Linux distributions and just packaging software. This means many applications would be maintaining multiple, let's say, minor versions at the same time. So Kubernetes is a good example where I think today there are 5 versions of Kubernetes from 128 to 131, 32. To be honest, I lost track of it a bit, but some AI/ML applications also have version streams, which means we have to package multiple of these apps. And again, yes, Python, I mentioned that. 5, I was correct. So anything from 3.9 to 3.13. And many applications do work with the latest versions, but that's not enough because sometimes we also need to package specific versions because, again, people may be running models or people may be running code that requires an older version. And it's not trivial. So this may mean that we will actually be shipping multiple versions, right? So, and this is not all, right? So I mentioned GPU hardware. For many apps, GPU and non-GPU applications behave very differently. TensorFlow is packaged differently. PyTorch, for example, from what I remember, loads different Python libraries or doesn't load some libraries unless a GPU is present. So we could package the same PyTorch, but then, for example, without GPU, we can't properly test the GPU functionality, or we can't even test if it loads. NVIDIA drivers. This should be a whole set of slides on its own because it's an interesting problem. So when we started looking into this, NVIDIA drivers were more challenging than today. Right now, there are 9 versions of NVIDIA drivers that we're looking at. So 11.8. And then anything from 12.1 to 12.8. The nice thing is, recently NVIDIA introduced the compat libraries. Maybe I'll explain what the problem with NVIDIA is. It's not on the slide. So the challenge is NVIDIA drivers have to match the host drivers, and the host drivers map all the way to hardware. So in the past, when you would be spinning up an AWS instance or Google Cloud instance or Azure instance with a GPU, it would come with a specific version of NVIDIA drivers, and then your version on the host, and then your version in the driver in the containers has to match the host. So we had to ship very different versions of drivers based on what the customers may be needing or where they would need to be running it. I believe the drivers could be older than what the host provides, so that's why shipping 11.8, which is quite old, was a good choice. Now, from starting with 12 point something, and I don't remember the exact number, NVIDIA started shipping compat libraries, which make it easier because then the driver could be newer than the host. But I remember initially we ran into some issues with it. I believe now it's no longer a problem, but it has been challenging to sort this out. And then again, Intel versus ARM, it would seem like it's just a compilation issue, but if you Google for specific versions of GCC, I believe anything below 12.5, and ARM and some include files, you find out there was this change in GCC that broke all of NVIDIA compilers, and we had to do some patching around that. So ARM, being a relatively new platform for GPU workloads, has a lot of problems that need to be solved. And again, based on those two slides, like ideally, we may want to provide all the variants of drivers, Python, applications, their version streams, GPU, CPU, but that's not what we are somewhere in between doing that and just shipping the latest, but we really want to be choosing the reasonable subset. And I believe just for PyTorch alone, we package over 20 different versions of the same version of PyTorch, because we package multiple versions of Python, multiple versions of the NVIDIA drivers, and also at Chainguard we provide developer and non-developer images, developer and production images, where the developer ones include additional packages. So that comes to over 20 different versions of the same image, of the same PyTorch that we have to build and test. And again, like coming at this image, what we would really want is to ship one version that is working for everybody, but it's not the case, so we ship a lot of various options and combinations that we have to deal with. Yes, and then actually I do have a few slides on GPU. I just don't have the charts of the support matrices for the drivers and everything. So one other thing we realized is testing the images is very different and quite challenging. So, and by the way, this is the Wikipedia image of a smoke test. This is where the word smoke test came from in the 19th century, where pipes were just tested by pushing smoke onto them. I had no idea until they've made those slides. But when we think about smaller images, again, going back to even Argo CD, the way you would test Argo CD end-to-end is to deploy Argo CD, have it deploy some different applications, like a Helm chart, like maybe something from Git, and basically point a browser or at least a curl towards some of the endpoints of the applications and see that they work. And it sounds complex, but to be honest, with a reasonable CI system, with reasonable automation, it's something that is very easy to do, and it's something that we do on a daily basis. And with GPU images, it's very different because, well, AI/ML apps have a lot of have quite a huge scope. So yes, we can test the basic things. We can test, I don't know, entry points. We can test that the applications load. That, I don't know, if I call torch.tensor when it generates, or tensor.run when it generates a random tensor, and it's actually loading enough libraries to talk to the GPU. I can test it this way, or we can test it this way. I'll automate that, but that's not really what our customers would be running. So, for example, an ideal test would be that we run a learning of a model and benchmark the time that it takes, benchmark that the results from that model are more or less similar, because AI is also non-deterministic. So we can't write a test where we teach it a model and then expect the model to always output exactly the same thing. But we could at least expect that the learning is successful and that the result is is within a set of results we think are reasonable, which if we, I don't know, calculate probabilities or a simple one-dimensional result, is actually doable. We are not there yet, to be honest. We have reasonable tests in place for AI/ML images today, but I think what would be ideal is very far from it. And again, like testing GPU, non-GPU, our pipelines are more optimized towards testing non-GPU workloads. So we do test the non-GPU features more extensively in the pipelines. For the GPU test, we also have some automations in place and test them, but it's very challenging. It's really difficult also to figure out what to test and how to do it. And so that if we build those 12 images, how do we run them without this running for multiple hours and being a very challenging thing to maintain and not be flaky. We don't test on all the hardware either. We test it on a subset of the hardware. We try to figure out where to run it. So right now, we focus on Intel, but we do have some tests for ARM as well, and we use public clouds, which is also kind of problematic, because one thing that I also expect, and this is mentioned here, is I'll start from the end of the slide because it's better to segue from there. If anybody's running something not in the cloud, we would have no way to fully reproduce that in an easy way. So we kind of try to figure out what's the best way to run things, what's the most common hardware across cloud that we should be testing. Obviously not the NVIDIA 5060 Ti, but it's a challenge to figure out all the scopes that should be tested. And yeah, so for now, the upside is for building, we don't actually need the GPU. So building the packages, building the images is quite easy. We just compile all the things from NVIDIA 10 to all the way to PyTorch. It takes a while, but it does build. And the NVIDIA compilers do not need a GPU to compile for all the variants. So it's quite good. That part is quite easy to do, but the actual testing of it is the challenge. So today we use GPU instances across 2 clouds to test those images. But like I said, ideally we would want to have a better coverage. It's just we are still trying to improve all the pipelines, and I think that's the case with everything at Chainguard. We've been packaging images for a while now. We've packaged quite a lot of them, but it's still something we are trying to improve. And AI/ML is quite challenging in that aspect. And right, and performance. That's what I mentioned. I don't think we do enough of testing of performance. So we do run the learning. We do run teaching the AI models to benchmark the speed. And there was actually quite an interesting fact that we realized when we did this. When we started experimenting with this for quite a while, we realized that using venv, at least for PyTorch, made it much, much slower, which was very surprising. So I don't know how many of you use or package Python applications. venv is a tool that allows shipping all of the Python packages in a subdirectory of an application, which makes it easier to, for example, ship multiple applications at the same time. And when we mentioned PyTorch being shipped along with Triton server or anything like that, this makes it a bit easier to manage dependencies. But we also realized that the performance difference was quite significant. I believe it was 20% slower, and we couldn't get to the bottom of why it's slower. But basically, shipping the libraries in USLib instead of shipping them in a venv was just significantly faster, and even in longer running processes. And this was one of the interesting findings that I don't think we ever figured out why, but it was something we stopped doing because of that, and it made a big difference in terms of how the images were running. And again, because packaging something and running some manual tests would be easy, but then getting to something that's fast, efficient, and well tested and has consistent performance was a bit more challenging. And I believe that is it. So thank you, everyone. Questions?
Any questions?
So I'm just curious how you maintain this entire environment and how you keep things updated.
So what we do is somewhat separate. We don't usually maintain all of environments. The way we build everything at Chainguard is we split into 2 steps. So we compile the source code into binaries, which are basically the APK packages. And for that, we don't even need the GPU, as I mentioned. This makes it slightly easier. The packages would have some tests, so we would actually test that the Python library is loaded, at least without the GPU at this point, and we can do that in any. Well, we don't use GitHub Actions or anything similar because of the scale, but we do have our own build environment that just spins instances one up and down for any single build, and that's also for security reasons, because often we would be literally cloning random code of the internet and compiling it, so we don't want to keep anything like that persistent across builds, not to contaminate them. But this is all set up and tear down per build. With the images, it's very similar setup. We build the images, we have our own tools for that just basically put an image based of multiple APK packages together, and then it's a valid OCI image. And for testing, we also spin up and tear down the environments for automated tests. Like I said, we don't have all the automation in place. For some of the tests, we have manual documentation for the more complex ones. And then it's before we release, there is a lot of automated tests being run. But today, for some of the more complex testing flows, when we, for example, refactor the application, we would have an engineer spin up an environment according to documentation, so according to specific, I don't know, say specific image in a specific cloud with specific GPU type or specific GPU types clouds, run some tests documented there, and that would be the criteria for it. And for example, merging that change to an image in and then having the automation build it again. So that's more or less how it works. But we don't maintain the environments. It's more about setting them up and tearing them down dynamically. We are now moving more towards using the cloud-managed Kubernetes clusters for these kinds of tests, but it's still a work in progress. There's a lot of things, like I said, that we want to improve in testing.
Thanks for the talk. You mentioned that you've been working with NVIDIA GPU specifically in trying to add hardware support. Have you also looked at the AMD side, specifically ROCm, and what kind of experiences do you have about that then, if so?
Sadly, no, the focus has been on NVIDIA so far. So
Okay.
just NVIDIA.
Any more questions? Okay. Thank you, Wojciech, very much.